Yeah, well, hi everyone, and welcome to my talk, in which I want to explore together with you, the audience, the potential of formal approaches to emergence for AI safety. Although I will be almost not using any formulae, it will be rather a technical talk. I'm going to say this right up front, just due to the stage I'm at with this project. But I do hope that those who can't make much sense of the technicalities, it will still be possible to take away some high-level ideas. And I also want to say right at the start that the word emergence is a frequently used and certainly overused word in all sorts of contexts, both scientific and colloquial. And I use the word emergence in a very specific way. The type of emergence that I target is the one that you see, for instance, in the moving shape of a flock of starlings, in the formation of galaxies, or in the way crowds behave, also in the way conscious human experience arises from lots of different neurons. So it is a dynamical type of emergence, one that unfolds over time and with probably pretty complex multi-scale relationships. So relationships between micro, meso, and macro scales of a system. I'll say a bit more on that in a bit. So what I wanted to do in this fellowship is to explore whether we can bring together various strands of research, philosophical, formal, empirical, on emergence to inform and bring progress on research in AI safety. The main question being whether measures of emergence could shed light on AI capabilities by characterizing or maybe even predicting or detecting them. More on that in a bit as well. My own background is computational neuroscience and complex systems, and my own expertise lies in both conceptual and empirical work on emergence. So this is my attempt to build bridges to AI safety. So here's a little overview. I'll first explain what emergence is. I'll properly introduce the project and the goals for the fellowship. I go into its outcomes, that is conclusions on benefits, feasibility, and future uncertainties. I'll end with a summary and a question for you, the audience, which will be, is it worth to pursue this research idea further? So it will be worth for you to pay attention. And I also ask you to bear in mind that this project is at quite a messy stage, in which both some narrowing down had happened, but also an opening up of new questions to explore. So naturally, there is some difficulty in presenting something clean, so to speak. So you can look at this presentation as something like a story of my research journey so far, and I hope it will be not too confusing. So as Clem has been mentioning, I'm not sure, I will not be there in the breakout session, unfortunately, but people can follow up with me after the talk via mail, so feel free to reach out. Okay, so I'm going to start with emergence. What is it? As a working definition, let's say that an emergent property occurs only in a collection of elements, but not in the individual elements themselves. So a very simple example is this circle here, which we call the macro scale, and it emerges from the set of the single points, which we call the micro scale. And a more complex example is given by this bird flocking here. So yeah, you usually see that the kind of emergence that the flock of birds displays is quite different from the one in the circle. It's as if the moving shape of the flock has a life of its own, and one might suspect that there's some interesting, quite complex relationship going on between scales. And what we target is the type of emergence we suspect to be happening in the flock, not the one in the circle of dots. So it's a particular subset of all possible micro-macro relationships, and one that is, importantly, dynamically so unfolding over time. Within the category of dynamical emergence that the flock is exhibiting, we can now, in a more fine-grained way, distinguish further characteristics of micro-macro relationships. And that is in terms of different kinds of information that the different scales entail. Information here is meant in the information theoretic sense. So for those of you not familiar with information theory, think of information as the answer to the question, knowing about some variable X, how much do we know then about another variable Y? That is the information that X has about Y. Okay, getting back to micro-macro relationships, imagine that we measure, let's say, the center of mass of the flock as the macro scale variable, and then the location of the single birds as the micro scale variables. One question we can then ask is how much information does the past of the flock carry about its own future evolution? If we don't need to go down scales and look at the micro scale to well predict the macro scale, we say that the macro scale is causally closed. It has something like a life of its own. Or we may ask, and it's a different type of micro-macro relationship here that we may target, is there maybe unique information that the macro scale has about its future evolution? That is, it can't be found elsewhere. It also can't be found in the micro scale. And if the answer here is yes, we call the macro scale causally emergent. The name here may be less intuitive, but don't worry about this. It's not crucial to understand the naming here. Just understand what type of information is targeted. So there are more types of micro-macro relationships, but it's those two types, causal closure and causal emergence, that I myself am mostly working with. So we call the different types of micro-macro relationships different facets of emergence. It's a definition that we make here, and measures of emergence operationalize those different micro-macro relationships, and they can indicate the degree to which a particular relationship is present. So that means they give us a continuous number, some positive score, indicating how strong that relationship is. So a few words on ontology, because I believe that anyone new to emergence, as presented here, will ask the question, does emergence really exist, or is it just a way to describe things we don't understand yet? A lot of people believe that if we had all knowledge about the lower levels, then we could explain the evolution of higher scales. There are counter arguments to this. For instance, the turtles all the way down problem, which basically points out that there is no natural ending of when to stop going down. And then as a response, some people might say, well, there's quantum physics and everything that exists is essentially following a wave function. I don't know, it might be. I personally have no ontological stance, but I also don't think it's that important, because even if ontological reductionism was true, I don't think that we'll be ever in a position to know everything, because knowledge is fundamentally perspectival. So I myself, I treat emergence more from a model lens, so to speak, model lens perspective. And I believe that measures of emergence, or the concept of emergence, including the measures, they will be useful no matter one's ontological stance, because micro-macro relationships, I think they will remain to be meaningful in making sense of the world, and so it'll remain worthwhile to do science on those. Okay, so let's get to AI safety. As I've been saying, I wanted to explore whether measures of emergence can inform research in AI safety by characterizing micro-macro relationships and also quantifying them. And that might be useful because macro scales in AIs, for instance, feature circuits that evolve during training, they do relate to their capabilities or to other relevant features. For instance, capabilities such as image generation or more sophisticated planning capabilities up to any type of agential behavior. And so being able to characterize those micro-macro relationships and maybe even detect, predict, and control them, that could help us to navigate potential risks that come from AI that display increasingly sophisticated capabilities. So to get the questions here very clear, the first is, what micro-macro relationships do we find in AIs, both qualitatively and quantitatively? So can we end up, for instance, with a classification of different AIs according to the micro-macro relationships, and how are the macro scales related to relevant capabilities? And then second question, once we do have a good mapping of types of AIs to the corresponding micro-macro relationships, can we detect or predict certain micro-macro relationships, and also following that certain capabilities in similar AIs? Once we have accurate and reliable predictions around those micro-macro relationships, the next question would be, can we use that knowledge to prevent certain micro-macro relationships because we believe, for instance, they are not safe or not wanted? And then finally, and very ambitiously, it's a question to be targeted in quite some time in the future. Can we channel the gained insights into something like eval's type of work to produce what I call here a deployable emergence assessment pipeline, so as to assess AIs with respect to their emergent macro scales / capabilities? So each network may have its own unique emergence profile, so to speak, that is delivered via a pipeline that is ideally as standardized as possible. And an emergence profile, just to give an idea, it might include the type and strength of the micro-macro relationship, the relation to the capabilities. So for instance, network A has capabilities X, Y, Z and high causal closure. And let's say network B has capabilities A, B, C and low causal closure. Then as a last question, I think what one could target is asking whether it's possible to synthesize all the gained knowledge from questions 1 to 4 to safely enable the discovery of yet unseen capabilities in unknown models. So for instance, imagine we build a really new model with an unseen architecture and maybe a new size, and we observe that causal closure rises during training. Then, depending on what we know about micro-macro relationships in those networks, that might give us reason to pause, because we might suspect some powerful capability emerging. So these are all preliminary questions, and I think they give potentially a decade-long research program project. So with multiple iterations going from questions 1 to 5. Yeah, so it can be quite, it's yeah, as outlined here, it's quite a big thing. A few remarks that I want to give here on those questions. So the way I've depicted how emergence research might inform AI safety is too vague yet. So the exact risk landscape, as well as space of possibly emergence-related strategies, that would need to be fully explored. And it's also important to make very clear that what underlies these questions is that in AI's macro scales, they will relate to the AI's capabilities or other relevant features. Now, it is important to say that what constitutes a capability or something we call a relevant feature essentially is in the eye of the beholder, that is in the eye of us humans. So I think that expert domain knowledge in this type of investigation will always need to be in the loop. And I say this, I say this because some might have the hope that we'll at some point be able to fully automatically, purely quantitatively discover an emergent capability. But I believe we will always need to refer back to our qualitative assessments, because we somehow need to perceive the emergent thing as such. So for instance, we need to see the flock, or we need to see the practical relevance of an AI's capabilities. So no quantitative assessment will be able to guarantee that some identified macro relationship has meaning to us or bears relevant to us. So this is something that we always need to decide upon. Okay, so regarding question number 1 from the list, one possible avenue I saw to tackle it was to identify one generally agreed upon emerging capability in a neural network, and then investigate whether emergence measures would be able to capture them. This is a rough goal, and a lot of questions would still need to be specified. So for instance, what phenomenon and what model, bigger or smaller, to look at. So here, the general risk of small toy models is that we miss the phenomenon we're actually interested in, or that measures of emergence will capture things only in bigger models. And the risk of big models, in turn, is that they are computationally too expensive, or it's not possible to do rigorous science with them because there are too many unknowns, too many confounding variables. Then another question is how to apply information theoretic measures of emergence to AI. So they have all sorts of requirements, and it can be a science in and of itself to make them work. So yeah, the question is there a feasible way? I will get to that in more detail in a little bit. So this is roughly where I was at when I started the fellowship. I will now talk about the progress I've made over the summer, and yeah, I will first say a bit on the motivational side of things, because over the course of time, I did a bit of rethinking on what the aim and value of this research idea would be in the first place, based on lots of conversations I had with people. So first, why emergence in the first place? Why is seeing things through the lens of emergence good? This is a more general question, so going beyond the question of how useful measures of emergence are in particular. And a short answer is related to what I had previously said about reductionism. A short answer is that the world is fundamentally organized in scales, and it seems that a lot of important features come about at higher scales. So no matter what we believe is ontologically true, our human mind operates with concepts like causality or hierarchical micro-macro relationships. So they are quite fundamental for our thinking. And I would also say for our actions, in fact, because, for instance, in order for me to predict someone's next action, I wouldn't look at all the billions of molecules the person consists of, but just at a few macro scale features, for instance, their facial expression or the words that they utter. So yeah, both being able to understand and being able to act in the world requires us to coarse grain, that is, to see things at different scales. I think an interesting sub-question here would be whether AI cognition could work differently, that is, whether AIs could have more flexibility as to when to coarse grain and when to go down levels. Because, for instance, going down levels in one case and not in the other, that might give better outcomes for the task at hand. So engineered systems have more compute that could be exploited, and so they could, more than humans, afford to look at things at the micro rather than the macro scale, if that turned out to be more useful for solving a task. Okay, a second point on motivation is the question of what the deal is for evals. Neil Nanda prompted me with the question of what the benefit of using measures of emergence to shed light on capabilities would be if we could design a good benchmark instead. That's a very fair question, and a tentative answer to that is threefold. So first, there is a general benefit of understanding. This project is more on the interpretability side of things, so figuring out what's going on internally. And I think mapping certain micro-macro relationships inside a network to its behavior is valuable in and of itself. But this is only the first step. So once we have a good taxonomy of micro-macro relationships in AI, that mapping might help us to eventually bridge the gap to not only characterize an AI's behavior, but also predict and manipulate the capabilities in similar AIs. And finally, it is also possible that measures of emergence point to some capability in an AI for which we can't come up with a good benchmark, or also to some capability in a new model of which we don't know yet what it is about. So to restate the scenario I had been describing already before, let's say hypothetically, we observe that some subset of networks with certain architectures have high causal closure. And let's also say that it's also those networks that display more powerful capabilities. Then let's also say that causal closure scales with bigger and more capable neural networks. We might then also see that high causal closure evolves during training in a new, even bigger network that we don't understand enough of yet. So we can't say yet what capability the network possesses, but because of our really well done previous emergence research that is extensive, comprehensive, robust, reproducible, etc., we have come up with a certain taxonomy of micro-macro relationships. And so we might have reason to believe that the capability evolving in this new network is a powerful one. And we might want to hold and choose the next step more carefully. So all of that is in principle possible, but there is this very clear first step, which is investigating whether measures of emergence can pick up on known macro features that relate to known capabilities. Once we've seen that the measures are robust, accurate, reliable, well-established in various applications, we can proceed to cases with more unknowns. That path generally is quite effortful, the path outlined here. And yeah, the road to eval's type of work is certainly more uncertain than I initially was acknowledging. But yeah, these are the possibilities. Then last, as a third point on the motivational side of things, we can ask why statistical measures of emergence rather than more strictly causal analyses, which are already possible in neural networks. So here, generally, it's the case that information theoretic measures are quite powerful in describing all sorts of relationships. So for instance, linear, nonlinear, but also more qualitatively in terms of, for instance, redundancy or synergy. And you otherwise don't have a language for that. And it might also be the case that correlational analyses are computationally cheaper in certain scenarios compared to causal ones. And sometimes it also might suffice to use a to look at a correlational relationship. If it's strong and robust enough, yeah, it might be enough for whatever we're trying to achieve. Okay, a few things now that I want to say about feasibility. How do we know that we have found a feasible setup to investigate measures of emergence? Saying that those measures are or are not feasible is quite a strong claim. So what would be the criteria for something to be or to not be feasible? I want to say as a first thing that whether something is feasible is always a trade-off between what can be gained versus what does it take to get the gain. So for instance, if the thing we're actually interested in exists only in the big models, we simply would miss the point if we conducted a range of applications in the small models. And feasibility would be even more impaired if those applications in the small models are costly. Let's say the time on getting the application right, is long, making it scientifically rigorous is costly, stuff like that. Then there is uncertainty around knowing whether a measure of emergence has worked due to the lack of having something like ground truths available to us. So it's not like we can safely say, this is an emergent phenomenon and our measure needs to be able to detect this. With emergence, we're at a stage that the concept of temperature was in roughly 150 years ago. I don't know if I get the time here right, but we now know what temperature is, and we have good measurement devices for it. But that was not the case in the past. So the concept of temperature didn't exist, and we literally invented it in an effortful back and forth in science with a lot of confusion and frustration. So one could say that this is what currently starts to happen in a way with emergence, although I expect this process to be way more convoluted and complicated than in the case of temperature. In that context, I highly recommend to read Inventing Temperature by Ha-Seok Chang. It's very insightful with respect to how science progresses when there is nothing or almost nothing to rely on. And funnily, just a few days ago, there was a blog post by Adam Shimi who had recommended that book as well. Yeah, so then finally, as a third thing on feasibility, there is uncertainty around the technicalities or the implementational side of things. I've been hearing from some people about some frustration around information theoretic measures, and I totally get that. I've been working with them a lot. It can be very frustrating. Where, yeah, people have been saying that either there is a good tool applied in some domain and it works so that we can transfer it to another domain, or the tool doesn't work and it's more complicated, in which case we shouldn't use it. So the thing with information theoretic measures is that it's neither the case that they don't work at all, nor that they work well. It's more like they can be made to work if really carefully and scientifically rigorously applied, possibly including workarounds. Sometimes a workaround is not possible, in which case time might be better spent to derive new tools. Which avenue to pursue is not clear up front. So that is something that needs to be explored. It's exactly that friction point of finding a workaround versus building a new tool that needs to be navigated here. An important takeaway question that I was prompted with by Rory Gray, my mentor, and that is, I think, important to always bear in mind is what is the fastest, emphasis on fastest, what are the fastest ways to invalidate this project, both conceptually and also in the implementation? So put differently, what would be the fastest way of implementing something and knowing it has worked? What would be a good feedback signal? I believe that with a project that is that much at the edge of scientific knowledge, so with that little to rely on, we really need a lot of brains and a lot of perspectives to get a hold on that question. Okay, I will now get to some of the technical uncertainties I wanted to make progress on, and I will explain those using an operationalization of the idea of causal closure, what I've been explaining before. It's called dynamical independence, in short, DI. And it can be written down like this. This is the only sort of mathematical expression I use throughout the presentation. So what do we have here? So imagine we have a time series of macroscale, a macroscale variable and a microscale variables. So we measure those over time. T and t minus 1 refer to two different time points. The I here refers to the information between what's to the left and to the right of the semicolon. We don't need to go further into what information mathematically is. The stroke here means we condition our expression on the macroscale variable at the previous time point, t-1. So what is it that we're looking at here? We do look at the information that the microvariables have at some past time point about the macro variable at the current time point. Importantly, given we already know about the past of the macro variable. So if that quantity goes to 0, then we have a macro variable that is equally good in predicting itself compared to the micro variables. It's like a macro variable that is causally closed. We would also alternatively call it dynamically independent here. So yeah, referring to the name of the measure, dynamical independence. Okay. So this is one operationalization of the idea of causal closure using information theoretic language. Regarding the technical uncertainties, so one is stochasticity. Dynamical independence is defined for stochastic processes, that is for a sequence of random events. So the question then is there a way to see neural networks as involving some kind of random element? Another is Gaussianity and linearity. If we can, we should use formulae for dynamic independence that require the process to be Gaussian. So is there a way to get a Gaussian process, or if not, can we make it Gaussian? And as we deal with processes, can we somehow get a time series of our chosen micro and macro scales? Then we also have stationarity. The stochastic process is supposed to be stationary. That is, the distribution of the variables does not change over time. Can we get that? Another problem is system size. What are the computational costs in computing dynamic independence, depending on system size? What systems can we currently apply it to? How scalable is it? Those kinds of questions. Then there exist both parametric and non-parametric solutions for dynamical independence. I will not explain what that means. It's just another factor to bear in mind. Then finally, the big question is, can we find a mapping from a higher dimensional micro to a lower dimensional macro that can be also linked to some meaningful capability? And that also satisfies all the other things I've been just talking about. I'll be addressing those uncertainties using LLMs as the example neural network. It's simply because I've been mainly thinking about LLMs. And by addressing those uncertainties, you'll also learn what an implementation of something like dynamical independence could be. So I will present a setup that looks promising, I think, and I will start by first addressing Gaussianity. So normally, the nodes activations are not Gaussian. That is, they are not normally distributed. First option that comes to mind is whether we can transform the data such that it gets Gaussian. That often does not work. Then some people are working on solutions that would free us from the Gaussian requirement, but that is pretty much work in progress. We can't use that now. And after quite a bit of thinking, together with Guillaume Corluer, the thought came up that we could use the magic of the central limit theorem. So the central limit theorem states that no matter the type of data points, the type of the distribution of the data points or the bigger data set, in the case of infinite data points, the distribution of the means of those data points will converge to a Gaussian distribution. But only if it's the case that they are IID, so independently distributed. What does the other I stand for? So it means that they can't be correlated from each other with each other, so that's the important bit. And the sample needs to be large, and the variance needs to be finite. So the problem is that most of the data is not independently distributed. So we need to ask, at what point is the data separate enough from some other data to be considered independent? We did come up with a setting that might work. So we can view an individual prompt to an LLM, including the activations and outputs it causes, as independent from other prompts, activations, or outputs, and as coming from the same distribution, which is the totality of human language. Oh, actually, I remember IID, independently and identically distributed data. So yeah, coming from the same distribution and not correlated with each other. Okay, so in that setup, one observation could refer to the activations of a single layer or the totality of the network. The mean of all observations will follow in the limit a Gaussian distribution. Following a prompt, we'd get something like a sequence of tokens that will yield something like a time series of the node activations. If we now generated a large sample of prompts, the means of those time series of node activations across token positions would follow a Gaussian distribution. That is something we can exploit. That enables us to look at dynamical independence for pairs of layers or for pairs of token positions. What does that mean? I'll explain that. So regarding the first option, we could use the mean vector of 2 layers as an input for dynamical independence by making use of something like a mathematical trick, so to speak. So those 2 vectors are technically not a time series. They don't depict a time series, but we can still use them for our calculations of causal closure as operationalized by dynamic independence. So doing so for each pair of layers, we could showcase changes of dynamical independence across different inference steps within the network. That is just one possibility. Another would be that alternatively, we could generate means across layers and use the mean vector of 2 token positions as an input for dynamical independence. In that case, doing so for each pair of token positions could show changes of dynamic independence across the different stages in the production of text following a single prompt. Finally, we could do both for networks at different stages in training. So we do have quite a few possibilities here. I know this is a lot and probably complicated to understand without visualizations. I unfortunately didn't have the time to generate one, but for now, maybe just remember we could compute dynamical independence, so causal closure for pairs of layers or for pairs of token positions, and see what changes do we see. Okay, in this setup, we've actually solved the stationarity problem, as the distributions we look at here are Gaussian and they remain Gaussian. And the node activations indeed can be viewed as random variables coming from a stochastic process, because the input data is a random variable and the node's activations are a function of the data. Regarding the system size, that is something that still needs to be figured out. So LLMs, they have billions of nodes. The smallest systems still have lots of nodes. If we focused only just on one layer, we could decrease the size to, let's say, a few hundred, but that still might be too much. Generally, one strategy could be to randomly sample nodes or group them. Some studies do that, in fact. But it does introduce certain biases that we ideally don't want to have. Dynamical independence might be scalable. It depends really a lot on how dynamical independence is calculated. And having looked into this a little bit, it turns out that measuring the scalability of dynamical independence via the big O notation would be an own little research project. Then, regarding the mapping from a higher dimensional micro to a lower dimensional macro, that also relates to some capability, I did realize that which macro scales in AI relate to their capabilities is generally a big question. In a way, that's one of the core questions in technical AI safety. We are not there yet. We still need to establish those links between internal macro structures and capabilities in the first place. So it's another unknown to deal with. But we have something like options. So just to illustrate a conceptual example here of what that could be. So let's say a vertical line is one feature, it's represented by one node. A horizontal line is another feature, it's represented by another node. And their composition gives a third feature, let's say a rectangle, which is also represented by another node. And that third feature is somewhat emerging from the other two. And all three nodes together give something like a feature circuit. If we were now able to obtain something like a lower dimensional coarse graining from that feature circuit, we could apply dynamic independence to that micro-macro pair. So the top suggestions that I so far got, mainly because those are well-known phenomena and the models are small. For instance, macro circuits and context learning. So for instance, curve circuits where the microscale would be the individual attention heads. The macroscale would be attention patterns like induction heads, line following heads, or quotation marking heads. Another example would be image classification in CNNs, where the microscale would be the individual convolutional filters in the early layers, and the macroscale, the higher level features in the later layers, for instance, parts of objects or whole objects. Then there are also progress measures for grokking, a paper by Neil Nanda and others that shows how generalizing emerges during training. And there is some summary statistic of some macro variable involved, and that might be a good candidate macro scale. But it's something I would need to have a look at, a closer look at yet. So it's nothing that I delved into. So what macro pair to look at in what network is a big question, and I just dipped my toes into it. Another uncertainty that I, again, got aware of relates to confounding variables, which measures of emergence are susceptible to. So what could confound a micro-macro relationship in a neural network? It's a very important question to think about in that type of investigation. I want to share also some more overarching thoughts, a few things on the necessity to use toy models. So while I was aware that measures of emergence might simply not pick up on emergent capabilities in small models, I came to believe that there is probably no other way around using small toy models first, because we need something where as much as possible is known and controllable, as this is what allows us to do the most rigorous science. Progress is easiest if all but one piece of the puzzle is known and well understood. At least in this type of project, might be different in others. Also, if results are completely nonsensical in the small model, we probably have reason to doubt it would be any different in the bigger model. It might also be that if we can't find a good toy model where things are well controlled, or at least controlled enough, we might need to build that toy model in the first place. So a few uncertainties that will remain until we have experimental results or more clarity around the technicalities I've been talking about. So one is the relevance of information theoretic measures outside of science. So there are doubts that information theory measures can be really useful for anything else than science. For instance, because effect sizes are small or the applications are too difficult, costly, inaccurate, etc. If we can't make them work, we might think about other measures to link macro scales to capabilities. And then in the scenario that measures of emergence do give sensible results in small toy models, we'd need to hope that we can, in some way, bridge the gap to bigger models. What this bridge looks like is not clear. So, a little summary. What do we gain? What are the hopes with measures of emergence? We want to use them to further characterize known internal macroscales in the network to known capabilities. We want to advance the prediction and manipulation of those macroscales in similar AIs. And we also might even want to get to a situation where they can help us in navigating unknown capabilities in new, very different models. Is there a feasible implementation? What would be the fastest way of implementing something and knowing it has worked? The short answer is that we should use a toy model that we do know a lot about, that have interpretable macro scales as a starting point. I've been mentioning a few ideas here, and we should then proceed from there. So I've been working on this 6 weeks full time, and I am happy about having reduced uncertainty in some really big questions. In general, I want to emphasize that it takes a village and a lot of patience to get to answers. So I want to express something like a pledge for cooperation between scientists and engineers. And I envision pairing scientific rigor, which mostly comes from academia, with practical relevance and actions, which, well, mostly exists outside of it. But also, we must not forget that we need to be more inventive and adventurous than the modern scientific method would let us believe. A quote from the blog post that I've been previously mentioning from Adam Shimi. And I would like to hear from you, maybe if you have ideas, whether you'd like to see this project being pursued further or not. And I want to say thank you for your attention. And a big thank you to Rory Gregg for his mentorship, in particular also for navigating the intricate problem space in AI safety more generally, Guillaume Corluer for in-depth discussions on very intricate, hair-raising mathematical issues, Neil Nanda, Vikrant Varma, as well as Clem von Stengel for discussions around macroscales in particular, and PIBBSS in general for giving me the opportunity to explore this research idea. Thanks a lot.
Thank you, Nadine. All right, good people. It is time for Q&As. We have about 9 minutes before the next speaker. So please raise your hand if you would like to talk. I will allow you to unmute, and then you can ask some questions. In the meantime, is there something exciting that you learned during the last 3 months that you didn't get to share in the PPT because it seemed irrelevant, but you're actually excited by it?
I mean, I've been now talking for quite some time, right?
Fair enough. You had a lot of time to share.
I feel I've been sharing a lot on what I've been learning. I mean, the whole I think, as I've said, the presentation is something like a journey report. I feel it feels like that to me. And so, so I've been sharing much of what had happened. What else? I'm not sure. I would need to think about
Sure.
that.
You'll come back to me. All right. Let's see. Richard has a question. Richard, you can now unmute.
Awesome presentation, Nadine. Question on the tendency within models like LLMs as they get bigger, the type of emergence that we see sometimes is sort of actually a gradual emergence, as opposed to a very like shock point in time when we start looking at like the constituent types of subcapabilities that are starting to get better and better to come to an actual capability in the end. Um, is there something, is there some relationship between that tendency and what it is that you are looking at here, that you'd like to comment on?
So do you mean those things evolving during training? Are you talking about the training process?
Well, it's actually both, right? It's as models get larger in terms of like choosing to train larger models,
Mm-hmm.
but also like during training, things sort of percolate into place.
Mm-hmm. Yeah, so I don't know, maybe because I'm not sure how well I could express the ideas here, but um, the main idea I had was to um, look at something like dynamical independence, which is an operationalization of causal closure, one type of emergence, at different time points, either in training or in whatever else you might have a time series of, so to speak. So you can look at the evolution, at the changes of those measures of emergence. So whatever changes you see, the ones you've been now describing, that could be reflected in how measures of emergence evolve as well over time. Does that answer your question?
Partially, thank you.
Awesome. Any more questions? Once, twice, three times? No, Richard, for another one. Go ahead.
Um, is there any sort of qualitative difference in within that taxonomy that you would look at creating on the relationships between the levels, between static models and ones that do continual learning?
I mean, that would need to be well, I think this is an empirical question that would need to be seen. So there might be qualitative differences in the micro-macro relationships. So I've been just mentioning two different concepts. One was causal closure, the other I was calling unique information. So information you'll find only in the macro scale. It's nowhere else. And that might be a difference you find in between networks, including those that continue learning and those that are static. But I don't know. It's something to empirically investigate.
Is there some good list somewhere of like all the candidate properties?
Yes, there is. So in fact, together with a collaborator, we are about to publish a paper exactly on that. So something like an overview of the different micro-macro relationships that we label as some type of emergence, and what the corresponding metrics are, the corresponding information theoretic metrics. Outside of that, there are the papers that introduce the single measures. So yeah, there are certainly that they are there. Papers that introduce the single measures. The one that gives the overarching overview will come soon, but yeah, I'm happy to provide the literature for the single concepts, including their measures.
Awesome. When is that paper coming out?
I am hesitant to name an exact date, but it should be in the coming months. Like definitely this year, in the coming months at some point. Yeah.
Okay. I joined late. Can you share your email again?
Sure. I will.
The email is in the chat.
Awesome.
Yeah.
Thank you.
The email's
Also
in the
for
chat,
people
yeah.
who
Well,
didn't,
nice.
yeah, catch them time from the PPT.
Awesome. Thank you.
Sweet. Any last thoughts? We have 2 more minutes. No questions? None. All right. Thank you very much, Nadine. We are off for
Thank you,
a
Simon.
2-minute break, and then we're back with Sean.
Bye.